Swayam Prabha. Digital India. Educated India.
So, in today's lecture we will continue with the phasor computation using DFT, and then we will complete this topic and then go on to the estimation of system frequency using DFT. Okay. So, now we stopped here last time. We came to this expression here that a component is introduced e raised to j 2 pi by n w, which leads to the phasor rotation occurring with each window. Okay, like we gave an example of say n equal to 12, then with each new window phasor rotation of 30 degrees will happen. So, that has to be avoided. We need this expression only x e raised to j phi. So, that was it here. So, what do we do? We multiply both sides by e raised to minus j w is equal to. So, this is what we want, the RHS is what we want. Okay. So, now what is the LHS here? We will just expand on the LHS and see what can be done, or rather what happens if we expand this LHS. So, what is the LHS here? 2 by n k is equal to 0 to n minus 1 x of k plus w e raised to this is k. W. This term has got added on the left hand side. This was our original expression here. Okay, if you remember, this is what we started with. Okay. So, now if we see here x of k plus w okay. So, if you see here k, this is the index here is k plus w, here k plus w. So, we can as well change this k to start from w and end at w plus n minus 1. Okay, and then this can be simply x k. Okay. So, with this change of index, we have got rid of the phasor rotation. Okay. So, this is what we get back to the slides here. So, we change the index instead of 0 to n minus 1, we change the index from 0 to w plus n minus 1. If we had to, if the last window was used, of course, if rather the window number was the number of the last sample, then of course we will have to change the window number. You can do a similar process, but you will have to change the number, the index from W minus n plus 1 to W. Okay. Now, yes. So, this after elimination of phasor rotation we will have same thing. So, x e W is 2 by n x k cos of 2 pi. Notice here that the k plus W or the cos of 2 pi by n W has vanished because of the change of index. Okay. Now, how do we do this more efficiently? Because you see every window, suppose there are 12 samples, then you have to do 12 multiplies and 12 adds. Okay. And what is the, if you see this in every window, what is happening? You know, if as the window shifts, if this was the first window, this was window number 1, this is this one is window number 2. So, if you see in between window number 1 and window number 2, what has happened is this sample has gone out, this sample has gone out and this sample has come in. Okay. x0 has gone out and x12 has come in. So, for a change of just 2, repeating the entire calculation 24 times, and 24 times is for a 12 sample. If it is 16 samples, then 32 times, or if it is 20 samples, then 40 times is computationally inefficient. Okay. So, you can better understand it with the help of a figure. So, we see here that the difference between Xc of W m, or m is just used to generalize because we are basically interested in m is equal to 1, but just to generalize we have used m here, and you can see that the same thing that we talked about. Okay. So, we have this part of the between the difference between Xc W of m and Xc W plus 1 of m. I am dropping the index m just for convenience. So, the difference between Xc W and Xc W plus 1 is that this term here, x this multiplication x of W cos of 2 pi W m by n, okay, this goes out and this addition comes in. Okay, x of W plus n cos of 2 pi by n, n plus W of m, this one comes in. Okay. So, what we have to do, this rest of the part between the between this and this is common. So, what we have, the difference is what we have to do, we have to add this term and subtract this term. So, we will get Xc of W, provided we know, of course, we have Xc of W, then we will get Xc of W plus 1. Just add one term and remove one term. But if you see the term that is being added, it is cos of 2 pi by 2 pi by n, n plus W of m. Okay, because now we are going to W plus n here. So, what is cos of 2 pi by n, and n here will cancel. So, what is cos of 2 pi plus theta? Any theta will give me cos of theta only. So, in which case this is the same, this term, this cosine term, if you want we can write it here just for the sake of understanding. So, Xc W plus 1, I am dropping the index m, Xc W. Okay. So, what have we done? We have added one term x of W plus n cos of 2 pi n plus W. What was, I think there was something missing. Okay, yeah, m because m is not 1 here. Okay. And minus one term x of W cos of Okay. So, now what is happening is this term is the same as this, because cos of 2 theta plus pi is cos of cos of 2 pi plus theta is cos of theta itself. So, what we get, x c of w, x of w plus n minus x of w cos of okay. So, now you just have to this, and in case your phasor is stationary, that means this sample is the same as this sample, then you will get x c of w plus 1, which is what you would expect, because if your phasor is stationary, it is unchanging. You would expect this is what you will get. In case it is changing, because then why compute into the moving window format if it is stationary? You do not need to compute it at all. You can just do one computation and you are done. But the phasor is always changing, because there is loads are being changed, generators are coming in, coming out, there may be a fault. So, that is why this computation has now been simplified to just one add and one multiply computation. I mean 2 add 2 multiply in a sense, but just an update. So, the recursive form of the DFT is just an update. So, it becomes a very efficient way of computing DFT. Okay. So, now instead of we have now succeeded in making it into an update operation. Okay. Now, for the last sample everything is similar. If last sample meaning if we take here the subscript m has been dropped, or the index m has been dropped, that is why you get 2 pi n 2 pi w. Okay. So, this is what we derived. Okay. So, just says what it reduces computation from 2n multiply and add to 4 additions and 2 multiplications per update. Okay. Now, if we follow the last window convention, we will not do it here, but if you follow the last window convention, of course, you will have to change the, as we said, we will have to change the index from w minus and the lower, if you start the index from w minus n plus 1 to w, because the window number is the number of the last sample. So, it has to end at w obviously, and then there are n minus 1 samples or n samples there. So, w minus n plus 1. Okay. So, this is something that you can prove for yourself, only the index here will change, otherwise the expression is more or less the same. Okay. Now, there is another form, that is the half cycle form. Now, for half cycle DFT, why do we use it? Because to speed up the computation, instead of waiting for one full cycle for a 50 hertz signal, that would be 20 milliseconds, then that much time is lost in taking the protection decision. CTs may saturate, there are so many other implications of slightly slower computation. So, we can use a half cycle DFT. We saw a half cycle DFT also earlier, half cycle Fourier algorithms, but the half cycle similar to the full cycle recursive DFT calculation, the half cycle will look like this. So, what we will have is just some few differences which you can note is now here remember that if you see, or w plus n minus 1, it is the same thing. Notice that n is the number of samples per half cycle. That is why we are able to use the same indexes, but since it is a half cycle, it will be only pi by n into k instead of 2 pi by n into k. So, if we expand this, similar to the other earlier treatment, there is nothing different that is happening here. Our sample is the same, root 2x that we did last time, cos of Notice that the effect of W is not there because we have changed the index here. Okay. So, same cos A cos B kind of 2 cos A cos B rather. So, that will give us root 2 x outside k is equal to W plus n minus 1 cos of now 2 pi n a k plus phi plus cos of phi. Okay. Again, this is a double frequency term over one time period, it will go to 0 and then this will sum up n times. So, we will get root 2 x cos of phi, and similarly x s w sin of minus root 2 x sin of phi. Okay. So, what happens to the recursive update? Just a small change here in the signs. Okay. So, you would have noticed that here earlier we had x w plus n and minus x of w. But here what happens is if you see the full cycle algorithm, okay, this is one full cycle and I am just drawing. So, this sample and the one sample after n which comes after n samples which will be identical. So, that is why we said x of w plus n minus x of w. Okay. However, if you take a half cycle algorithm, the sample here will be changed in sign. So, you will have to take x of w plus n plus of x w. Okay, that is the only change and of course, the instead of cos of 2 pi by you take here in the computation instead of cos of 2 pi by n k we take pi by n k. Okay. So, here for the update you will add instead of subtract. Okay. That is about it. So, okay. Here this is a typo, of course, it should be w plus n. Okay. So, if it is the latest window number or versus the first sample, window number of the first sample. Okay. So, you can do this and see for yourself. We will end phasor computation using DFT here at this point. We will now begin with a new topic which is estimation of system frequency. Okay. So, this topic involves a few subtopics in that sense. So, we will for going to estimation or rather estimating system frequency, what we will cover is DFT of complex exponential. From that we will have a look at DFT leakage after we develop the DFT of a complex exponential. Then we will from the DFT leakage, of course, DFT leakage will be both magnitude leakage and phase angle. Okay. Then of course, the real world signals are not complex exponentials. So, we will then look at this is the motivation for this is just to develop the theory, then we will use it in DFT of cosine signal. Okay. then we will use the moving window approach, which we call generalized DFT. Generalized DFT is not a universally used term, it is just that we are using it for a sort of convenience. It is actually a moving window approach. So, generalized DFT of complex exponential. This is the moving window approach, similar to what we did in the earlier DFT computation, moving window approach. We first developed the theory and then then went into the moving window approach. Then generalized DFT or moving window form of DFT of cosine signal. Then estimation of system frequency or system frequency estimation for single phase systems. We will see how this is an approximate approach, and then finally, that is our final goal in this, not in this lecture, because we will, since this involves quite a few subtopics, we may not be able to finish it in one lecture. So, we will over the spread over next 2-3, this one and maybe 1 or 2 more lectures for 3 phase systems. Okay. So, the treatment here is a little more mathematically involved than what we have been doing so far. We will invoke things like sinc functions and all that, but it is not, though it is involved, it is not, I mean, nothing to be afraid of. It can be, you can look at it as a little more rigorous, but more fun also in that sense. Okay. So, now let us start with the DFT of complex exponential. Okay. So, complex exponential means the signal, okay, let us write it down. Okay. So, x of t is e raised to j omega naught of t or e raised to j 2 pi f naught of t. F naught is the nominal system frequency. We will see what happens if the frequency changes from f naught to f and all that. In fact, that is the whole motivation of this theory, is the nominal system frequency. Okay. Okay. And which of course implies that if x of n t s, that is the n sample, will be 2 pi f naught n t s. Okay. Now, what is our DFT expression? Our that we have been using for the past 3-4 classes. We must be very familiar with it by now. N is equal to 0 to n minus 1 x of n. Now, so far what we have been doing is we have been getting our n samples. Okay. What we said was we have been getting n samples per cycle or in one cycle. Okay. So, that is why if your nominal frequency was f naught, your sampling frequency was simply NF naught. So, if you had 12 samples per cycle, your sampling frequency for a 50 hertz system was 600 hertz, 16 samples was 800 hertz and so on. Okay. But now we will say that we get n samples in p number of cycles. Okay. Now, this p could be any positive real number 0.8, 1, 1.2. Okay. So, actually that will happen when your frequency will change. Okay. So, p is actually f by f naught. Okay. So, all our earlier theory was motivated with p is equal to 1, but here p is any positive real number. Point 0.8, whatever, 1, 1.2, anything could be. Okay. Now, the sampling time is n into Ts. Okay. So, we have is equal to p by f naught. Earlier, of course, it was p was 1. So, n Ts was equal to 1 by f naught. Okay. If p is equal for p is equal to 1. Okay. So, Ts is nothing but p by or in other words Fs is equal to n f naught upon p. Okay. So, now what are the what happens to the samples? We had said that, where was it? Yeah, we had said that x of NTS is this. Okay. So, this now we will plug into our DFT expression here. Okay. Sorry. Okay. X of n was x of NTS. So, that gives us e raised to, where was that, e raised to not NTS is to minus j . Now, this Ts here we will replace by p by n f naught. Okay. So, what will that give us? We will see. N and this is p by b n f naught. So, this n f naught and f naught will cancel. Okay. And you can see that this 2 pi small n by capital N is a common term here. Okay. So, f naught is eliminated from this DFT expression. Okay, so what will that further give us? What is that right? Okay. Okay. So, this is our DFT expression. Now, we will work on this and simplify this a bit further. Okay. Now, what are we doing? This is x of m. So, DFT at a frequency m. We are computing DFT at frequency m. So, what is I am sorry, what is the resolution on m? What does m is equal to 0 imply? Okay. So, m equal to 0 is a DC signal. Okay. So, frequency resolution is Fs by n is equal to f naught by p. Okay. So, for m equal to 1, for m equal to 1. Okay. So, actually it is m Fs by is or m f naught by p for m equal to 1. Okay. For m equal to 2, this is the fundamental of course. Okay. So, for m equal to 2, it will be 2 f naught by p and so on, 3 f naught by p and so on. Okay. So, now this this expression x of m, we will now simplify it further. What did we get? We got x of m is equal to 0 to n minus 1 e raised to j 2 pi by n p minus m. So, this part we take it out as a constant q. Okay. So, this simply becomes q raised to n, q is equal to e raised to j 2 pi by n p minus m. Okay. And this of course is a geometric series q square to q raised to n minus 1. Okay. Now, what is the summation of this series of the series can be written as a r raised to n upon 1 minus r. A in this case is 1, r is q. So, so we have 1 into 1 minus q raised to n upon 1 minus q. Is that correct? Okay. So, now what does that give us? 1 minus q is this, okay, 1 minus e raised to j 2 pi p minus m upon 1 minus e raised to j 2 pi by n p minus m. Is that correct? X of okay. Now, we will slightly modify this expression to write this. We will take it out as e raised to j pi p minus m as common and e raised to divided by e raised to j pi by n p minus m as common in the denominator, and here we will get e raised to minus j pi p minus m minus e raised to j pi p minus m divided by e raised to minus j pi by n p minus m j pi by n p minus m. Okay. Okay. So, now this is we are just simplifying it, e raised to j pi p minus m into 1 minus 1 by n. Okay. And this we are just multiplying by minus 1, the numerator and denominator. So, this will get flipped. Okay. Now, we use the simple identity, that is sin theta is equal to e raised to j theta minus e raised to minus j theta by 2j. Okay. Or in other words, e raised to j theta minus e raised to minus j 2 theta is 2j into sin theta. Okay. For the sin theta, the 2j's in the numerator and denominator will get cancelled. So, what we will be left with is sin of pi Okay. We will further modify this. Sinc, this is the sinc function, it is not sine. So, what it is you may be aware of, even if you are not, we will just see it very shortly. I will just write this expression and then this into this number, this here. Okay. So, this is basically what is sinc x. Some of you may be aware of sinc x, but the definition of sinc x is sin of x upon x. Or if you follow the MATLAB kind of definition, then MATLAB defines sinc x as sin of pi x upon pi x. You can use either definition, both are equivalent. Okay. So, now just a few properties of sinc x, because since we are on that right now. What is sinc of 0? Sinc of 0. Sinc of 0 is 1. How is that? You take sin of, there are various ways of doing it, but you take sin x is equal to 1 minus x cube by 3 factorial plus x 5 by 5 factorial, so on. So, sin of x by x, limit of x tends to 0, sin of x by x is equal to 1 minus, this is x. So, 1 minus x square by 3 factorial plus x 4 by 5 factorial, so on and so forth, which is equal to 1. So, sinc of 0 is 1. Okay. What is sinc of pi? Sinc of pi is, sin pi is 0. So, sinc of pi is 0. Similarly, sinc of 2 pi and all that is 0. So, how will the plot of sinc x look like? Like I said, this is pi, 2 pi, 3 pi, 4 pi, so on, and this is minus pi, minus 2 pi, and so on. So it will look like this is 1, okay, and then it will be reducing, okay. May not look like that here, but it will get smaller and smaller. The lobes will get smaller and smaller. Why is that? Because sin x alternates between plus minus 1, or rather it should not equal to sin x alternates between plus minus 1, and then as progressively as the denominator in the x is in the denominator, so the divisor gets bigger and bigger, this will get smaller and smaller. Okay. So, this is how the plot of sinc of x looks like. Okay. So, we will continue with our this. So, what does the simplified x of m, what does it look like? This will cancel, this portion will cancel with this portion, n will go up. So, you get x of m is equal to n e raised to j pi p minus m 1 minus 1 by n sinc of upon sinc of pi by n p minus of m. Okay. So, so this is the expression that we have got for the DFT of a complex exponential. Now, let us see what happens when for the fundamental frequency phasor, when m is equal to 1, p is equal to 1. Okay. What happens? This will of course, this will become equal to 1, then this is what? This will, the numerator is sinc of 0, because pi p minus m is 0, both are 1. So, this becomes 1, sinc of 0. So, this becomes 1, and this also is 1. So, what you get is x of 1 is equal to n. What this implies is there is no DFT leakage. Okay. Is this part clear? Okay. Now, let us see what happens if the frequency changes. Okay. Say the frequency changes from, suppose the frequency changes from f naught to f, say from 50 hertz to 51 hertz. Just a number, I mean you can work with f naught to f also. Now, the second thing is the sampling is fixed to n samples per or for one cycle of f naught, not f. Okay. You can, there are other techniques of changing it, but now we are here we are assuming that sampling is fixed to n samples per cycle of f naught. Okay. So, what does that imply? So, now at a frequency f instead of f naught or at the change frequency, n samples will be acquired in p cycles, okay, where p is equal to f by f naught. Okay. So, if f is 51, then p is equal to 51 by 50. I mean, just in that example, otherwise p is equal to f by f naught. Okay. Okay. Earlier you had n samples been acquired in one cycle. So, you could simply say that the sampling frequency was n f naught, which was say for 12 samples it was 600 hertz, for 16 sample 800 hertz. Now, the sampling frequency still remains 800, but now the system frequency has changed. So, it is now p is equal to f by f naught. So, n samples are because the sampling frequency is constant and the system frequency has changed. So, n samples are now acquired in f by f naught cycles. Okay. So, now to extract the phasor or the fundamental component, we will see what happens. Okay. Earlier we got for f equal to f naught, earlier we got x of 1 is equal to n, f equal to f naught. Okay, this was earlier. Now, we have f naught equal to f naught. Okay, so, we have x of 1 is n e raised to j pi p minus m 1 minus 1 by n sinc of pi p minus m on sinc of pi by n p minus m. So, instead of n you have this this component along with n. Okay. Earlier if there was no, if p was equal to 1, then this component we saw disappears and you are left with n. But since now this is present here, we get this is known as DFT leakage. This part is known as the magnitude leakage, and this part pi p minus m 1 minus 1 by n is the phase angle leakage. The magnitude leakage is a sinc of pi p minus m divided by sinc of pi by n p minus m. Okay. So, this is in of course, this is for this is not actually, this is x of m only, this is not x of 1, this is for frequency m, okay, mf naught by p. So, if for x is equal to say, we will just see a quick example for m is equal to 1 for the fundamental frequency, and say p is equal to 51 by 50. Okay, here x of 1, so m is equal to 1. Let us see what the magnitude and phase angle leakage looks like. So, we will see a plot of course next time, but we will just do this calculation quickly. So, x of if it was 50 hertz, we will just name it at 50. So, that is 12, and x of 51, at 51 what do we have? we have 12 into for the magnitude. Okay. So, magnitude of this is 12 into sinc of pi, p is 51 by 50 minus 1 upon sinc of pi by 12, 51 by 50 minus 1. Okay. So, this is 12 into sinc of pi by 12 into okay. This component, if you see, will be very small. Okay. So, at x no, it will not be, it will be 0.0065 or something. Okay. So, the DFT leakage is very small. Most of the energy will still be I am using the word energy just to denote that the phasor information will be still available in x 50. Okay. So, you will still though there is leakage in magnitude, it will be comparatively smaller. Okay. Oh no. Okay. No, this will yeah. So, this will be still be, I am sorry, there is a slight this it will be this. So, let us compute now what will happen if x of 51 minus x of 50. Okay. So, this you will get 12 will cancel, of course. So, you will get sinc of pi by 12, sinc of pi (51 by 50) minus 1 upon sinc of pi by 12, 51 by 50. Minus 1, approximately 0.0065. Okay. So, for small changes in frequency around nominal, the leakage is negligible. So, that is why you will see the DFT leakage plots next time, but you will see that around nominal the slope is 0. So, you know, the magnitude change is very small. Now, we will quickly see what the angle error is before we stop for the day, and then next time we will, in the next lecture we will see the DFT leakage plots and DFT of the cosine signal and continue. So, now what is the angle error? For the example that we took, pi p minus m to 1 minus 1 by n. So, it is pi, this is 51 by 50 minus 1 to 1 minus by 12. So, this is pi is 180 degrees, 181 by 50 into 11 by 12. This is approximately equal to 3.3 degrees. So, the though the magnitude error is not significant, there exists a significant angle error. So, we stop here today. We will see DFT plots, DFT of cosine signal and the rest of the theory for estimation of frequency, system frequency in the next lecture. Thank you.